How does alcohol make you drunk? Ethanol. This molecule, made of little more than a few carbon atoms, is responsible for your drunkenness. Often simply referred to as alcohol, ethanol is the activist ingredient in alcoholic beverage. Its abilities help it sneak across membranes and nestle into many different nooks, produce a wide range of effects compared to other clunkier molecules. So how exactly this causes drunkenness, and why does it have a dramatically different effects on different people? To answer these questions, we'll need to follow alcohol on a journey through the body. Alcohol lands in the stomach and is absorbed into the blood through the digestive tract, especially the small intestines. The contents of stomach impact alcohol's ability to get into the blood, because after eating, the pituitary sphincter, which separates the stomach's small intestines, closes. So the level of alcohol reaching the blood after a big meal might only be a quarter that from the same drunk on the empty stomach. From the blood, alcohol goes to the organs, especially those get to the most blood flow, the liver and the brain. It hits the liver first. An enzyme in the liver breaks down the alcohol molecules in two steps. First, the enzyme called ADase turns alcohol into acetaldehyde, which is toxic. Then, the enzyme called ALDase converts the toxic acetaldehyde non-toxic acetate. As the blood circulates, the liver eliminates alcohol continuously, but this first pass of elimination determines how much alcohol reaches the brain and other organs. Brain sensitivity is thus responsible for the emotional, cognitive, and behavioral effects of alcohol, otherwise known as drunkenness. Alcohol turns off the brain's primary brake, the neurotransmitter GABA, and turns down its primary gas, the neurotransmitter glutamate. This makes the neuron much less communicative and uses for relaxed or moderate doses for asleep at high doses and can compete the brain activity necessary for survival at toxic doses. Alcohol also stimulates a small group of neurons that extends from the midbrain to the nucleus accumbens, the reason importance for motivation. Like all addictive drugs, it prompts a squat of dopamine in the nucleus accumbens, which gives users a surge of pleasure. Alcohol also causes some neurons to synthesize and release endorphin. Endorphins help us calm down in response to stress or danger. Elevated level of endorphin contributes to the euphoria and relaxation associated with alcohol consumption. Finally, as the liver breakdown of alcohol outpaces the brain absorption, drunkenness fades away. Individual differences at any point of its journey can cause the people at more or less drunk. For example, a man and woman who made the same and drink the same amount during the identical meal will still have different blood alcohol concentrations, or BAC. This is because women tend to have less blood. Women generally have a high percentage of fat, which requires less blood than muscles. A smaller blood volume carrying the same amount of alcohol means the concentration will be higher for women. Genetic differences in the liver alcohol process enzyme also influence BAC, and regular drinking can increase the production of this enzyme, contributing to tolerate. On the other hand, those drink excessively for a long time may develop liver damage, which has the opposite effect. Meanwhile, genetic differences in dopamine, GABA, and dopamine transmission may contribute to risk to developing alcohol use disorder. Those with naturally low dopamine levels may self-medicate drinking. Some people have a higher risk for excessive drinking due to sensitive endorphin response to increase the pleasurable effects of alcohol. Others have a variation in GABA transmission that makes them especially sensitive to the sedative effects of alcohol, which decreases their risk of developing disorder drink. Meanwhile, the brain adapts to chronic alcohol consumption by reducing GABA, dopamine, and endorphin transmission and enhancing glutamine activity. This means regular drinkers tend to be anxious, have trouble sleeping, and experience less pleasure. These structural and functional changes can lead to disordered use when drinking feels normal, but not drinking is uncomfortable. It establishes a vicious cycle. So both genetic and previous experience impact how a person experiences alcohol, which means that some people are more prone to suspect drinking than others, and a history of consumption leads to neuro and behavioral changes. One more. Ethanol. This molecule, made of little more than a few carbon atoms, is responsible for drunkenness. Often simply referred to as alcohol, ethanol is the activist ingredient in an effort. It simply have to sneak across the membrane and nestle into many different nooks, producing a wide range of effects compared to other clunkier molecules. So how exactly does cause drunkenness? And why does it have a dramatically different effects on different people? To answer these questions, we need to follow alcohol and its journey through the body. Alcohol lands in the stomach and is absorbed into the blood through the digestive tract, especially the small intestines. The contents of stomachs impact alcohol's ability to get into the blood. The pylori finger, which separates the stomach. It has some problems, so speak again. And the stomach, and is absorbed into the blood through the digestive tract, especially the small intestines. The contents of the stomach impact alcohol's ability to get into the blood, because after eating, the pylori sphincter, which separates the stomach from the intestines, closes. So the level of alcohol reaching the blood after a big meal might only be a quarter that from the same drink on the empty stomach. From the blood, alcohol goes to the organs, especially those that get the most blood first, the liver and the brain. It hits the liver first, and enzymes in the liver break down the alcohol molecules in two steps. First, the enzyme called ADAs turns alcohol into acetaldehyde, which is toxic. Then, the enzyme called ALDAs converts the toxic acetohydrates to non-toxic acetate. As the blood circulates, the liver eliminates alcohol continuously, but this first pass of elimination determines how much alcohol reaches the brain and other organs. Brain sensitivity is the responsible for the emotional, cognitive, and behavioral effects of alcohol, otherwise known as drunkenness. Alcohol sounds the brain's primary brake, the neurotransmitter GABA, and turns down its primary gas, the neurotransmitter glutamate. This makes the neurons much less communicative and used to feel relaxed at the moderate doses, fall asleep at high doses, and can impede the brain activity necessary for survival at toxic doses. Alcohol also stimulates a small group of neurons that extends from the midbrain to the nucleus accumbens, a region important for motivation. Like all addictive drugs, it prompts a squat of dopamine in the mid-accumbens, which gives users a surge of pleasure. Alcohol also causes some neurons to synthesize and release endorphins. Endorphins serve as a calm down in response to stress or danger. Elevated level of endorphin contribute to euphoria and relaxation associated with alcohol consumption. Finally, as the liver breakdown of alcohol outpaces brain absorption, drunkenness fades away. Individual differences at any point in this journey can cause the people to be more or less drunk. For example, a man and woman will make the same and drink the same amount during the identical meal will still have different blood alcohol concentrations, or BAC. This is because women tend to have less blood. Women generally have a high percentage of the fat, which requires less blood than muscle. A smaller blood volume carrying the same amount of alcohol means the concentration will be higher for women. Genetic differences in the liver alcohol processing enzyme also influence BAC. And regular drinking can increase the production of this enzyme, contributing to tolerate. On the other hand, those that drink excessively for a long time may develop the liver damage, which can cause opposite effect. Meanwhile, genetic differences in dopamine, GABA, and dopamine transmission may contribute to risk for developing an alcohol use disorder. Those with naturally low dopamine and dopamine level may self-medicate through drinking. Some people have a high risk for excessive drinking due to sensitive dopamine response that increase the pleasurable effects of alcohol. Others have a variation in GABA transmission that makes them especially sensitive to the safety effects of alcohol, which decreases the risk of developing disordered drinking. Meanwhile, the brain adapts to chronic alcohol consumption by reducing GABA, dopamine, and endorphin transmission and enhancing glutamate activity. This means regular drunkards tend to be anxious, have trouble sleeping, and experience less pleasure. These structural and functional changes can lead to disordered use when drinking feels normal, when not drinking is uncomfortable, establishing a vicious cycle. So both genetic and previous experience impact how a person experiences alcohol, which means that some people are more prone to certain part of drinking than others, and the history of consumption leads to neuro and behavioral changes.